Hello everyone, and welcome back to our Chapter 2 notes here, where we're continuing our discussion, really an introduction, not so much, we're discussing all of the time, but we're not so much getting into the nitty-gritty of sets so far. We are really trying to nail down some of the terminology that we're going to use. So we've seen before this idea of basically how to just pronounce in English out loud an expression that has sets in there. We also saw our little symbol that means an element of, and so we can say something is an element of, is not an element of a set. Here we are going to talk about what will make sets be equal, what will make them be equivalent to each other, and we will introduce this idea of subsets. And so hopefully we will start to really get into doing some stuff with sets, having some really nice examples of applications of sets. And without any further ado, let's get into what makes sets be equal. Now in this case, for sets to be equal, they have to have exactly the same elements in there. Now, it's worthwhile to mention that elements inside of a set cannot be duplicated. So there's this idea of something that's called a multi-set, where you can duplicate items and it becomes a different set. But the elements of a set, if you have those elements appearing only once, for example, like this set with 1 and 2, this would be the same set as the one if you just have 1 getting repeated or 2 getting repeated. See, we wouldn't actually repeat these elements inside of here. These would be the same set. And it's not that they have the same number of elements at this point, if you just sit here and count them. It's because we would never write this set in this way, where we duplicate the sets. We would actually just rewrite it. We would rewrite with no duplications. We would just say, oh, that actually only has 1 and 2 in there. We would not duplicate them. Then you would say, yeah, of course, now 1 and 2, they're the same. And of course the order doesn't matter. So the set, if it has 2 and 1 in there, these are all the same, of course. Now, what we have for these sets, we have this kind of an attribute of having a different order. We're wondering, are these two sets equal right here with these different social media companies? We've got a couple of times, see there are two different sets here. One of them kind of ends there and the other one begins there. They both have Pinterest. This one actually duplicates Pinterest though, so we would just get rid of that one. We don't want to duplicate. Wow, do you see it also duplicates Flickr? Let's get it out of there. And then they both now, I thought it would duplicate it again. We don't need to get rid of both of them. So this one has Flickr, the other one has Flickr. They both have Facebook, they both have Twitter, they both have Vine, and then they both have Instagram. So actually, these are the exact same sets. Especially, it's apparent once we get rid of the duplicates. What about this set? This pair of sets, we're wondering, are they equal to each other? The set A, which is a set of all the citizens of the United States, and set B, which is a set of all the people born in the United States. Now, of course, the only way to be a citizen is not just to be born here. You can become a citizen by going through whatever kind of a naturalization process. And so there are plenty of citizens of the United States who are not actually born here. So, of course, these are not equal. They would have different elements. Here we get the most natural example would be Arnold Schwarzenegger. Cohagen, you got what you want to give the people the air. He was not born in the United States, but he is a citizen. He, in fact, was the governor. And so that would be an example of two sets that are not equal to each other. We have a different term, which sometimes we think in English that equivalent and equal, they're almost kind of like synonyms, but in the context of sets, we will not use them that way. They're not interchangeable at all. For sets to be equivalent, they only have to have the same number of elements. And here that's being defined in a very technical manner by saying that there should be a one-to-one correspondence between two sets. One-to-one correspondence basically means that you can pair or match elements together. Can match up one element from one set with exactly one element from another set. So we're matching up one element from the two sets, we're matching them up together from one set with one element from another. That would mean there's a one-to-one correspondence. And so we will see an example for this, but basically we could just think of it as meaning that they have the same number of elements, which of course you might as well get used to this type of a statement dealing with the cardinal numbers, saying the cardinal number of A is equal to the cardinal number of B. And so here we're wondering, do we have any kind of equality here, equivalence of sets? I notice a couple of duplicates. We can get rid of the extra C, we can get rid of the extra D that's in here. And now this set goes A, B, C, and D, and so these actually are equal. They have the exact same elements. Here this one goes 1, 2, 3, and this one goes 4, 5, 6. Obviously they don't have the same elements, but do you notice you can match up an element from this set with an element from that set for each one of them? You can match up the 1 with the 4, the 2 with the 5, and the 3 with the 6, for example. You can match them up like this. That would be a one-to-one correspondence, saying 1 matches up with 4, 2 matches up with 5, and 3 matches up with 6. This would be a one-to-one correspondence. But in general, we can just notice that they have the same cardinal number. The number of elements here is 3, and here there are 3 as well. And so they would be called equivalent. And then we will have a description for why those are equal and equivalent. Now we want to get into this idea of a subset. And so a subset is a set where the elements of the subset, so for example, if we want to say that A, this set A is a subset of the set B, then every single element that's inside of A has to be inside of B as well. That's what it means, a subset. It's like you're taking elements out of B, making a new set out of those elements, and it becomes a subset. And so we can use either the one that has the little line underneath there, or it's not really necessary all of the time. If you add the little line, to me it feels like this one means proper subset, where a proper subset, it should not be the same size. So if you think about the way that I described this one, that you're taking elements out of B and you're forming a new set, and that's going to be the set A, which is going to be a subset. Well, if you just took every single element out of B and you made a new set, well, actually you'd still just have the set B, but we actually have the fact that B is a subset of itself because all the elements out of B are also inside of B, so it doesn't mess up the definition that we have right here for a subset. Because what it's saying right here, A is a subset if every element of A is also an element of B. And so we could fill in B for here, and it will work. B is a subset of B, but B is not a proper subset of B. Proper subset means A is a proper subset of B if A is a subset of B and A is not equal to B. Then we will say that it's a proper subset. And here, I could be mixing these up a little bit. I think this one actually should be the one for subset, and then the proper subset will be the one that does not have the little line under there. Why don't we go with this one? Hopefully it's not going to come back to bite us, this mixing up of the notation, but it's a small note there. Mostly here trying to recognize what it means proper subset. It means it's not the whole thing. And so it's worthwhile to note, we're going to have a lot of symbols that are in the set theory that resemble symbols that we've used before whenever we're talking about numbers or whatever. And it kind of, this subset one, it should be reminiscent of this thing like less than or equal to. So if you say that a number is less than or equal to versus something being a subset, well, you could say with a subset that the cardinal number, for example, if A is a subset of B, then we should have that the cardinal number of A is less than or equal to the cardinal number of B, because we're just taking elements out of B and using A, so there's no way we're going to end up with more elements inside of A than what we had in B. And here, it might help us to remember what this symbol means. But here, why don't we take a look, figure out if these are subsets or not. We're wondering whether A is a subset of B. You notice every element from A, 1 is also inside of B. It's there. 2 is inside of there. 3 is inside of there. And so we actually will have that A is a subset of B. And then we have this one. Now, y'all are going to have to help me out on this one because I don't know that much about Academy Awards. I recognize these people. I don't know who Viola Davis is, though, to be honest. Have they all won Emmys? It's a wonderment. If they have, then it will be a subset. But we're about to find out right now that actually, yes, all of these individuals, they have won an Emmy, so it is a proper subset. We would say that A is a subset of the set E. And then moving on, we'll have here something that's going to be used very frequently in the coming sections, in section 2.3 and 2.4 and so forth, where we're going to represent a set as a Venn diagram. And sometimes, not only the Venn diagram, but I want to show you guys how you would represent using the bag diagram as well. I know that sometimes it can be kind of funny to come up with the bag diagram, where the Venn diagram is basically the same, it's just not as fun to draw a Venn diagram as it is to draw these bags. But they have different uses. So bag diagram, very quickly, what if you had a set that goes like 1, 2, and 3? Every time you have a set, you make a bag for it. And then you put the elements inside of there, like 1, 2, 3. So then if you had a set that goes like 1, 2, and then maybe also the empty set could be inside of there, then it would be such a bag that would have 1 and 2 in there, but then the empty set is a set, so we should make a bag for that one. So there's going to be kind of a bag inside of our bag, but it's empty. It's an empty set, so it's just an empty pouch floating around in our big bag there. Venn diagram we will use not really for sets that are standing alone, but we would want to use them to show where sets overlap, like where they share elements and so forth. And so here we're getting this idea about a proper subset, and so sure enough, this is the notation we're going to go with. Here goes proper subset, and here goes just subset in general. The proper subset, it will not include the whole thing there. And so we will have, let's see here, a little problem about the subsets. We're wondering, this table of medalist winners, we have, based on sports, we've got different sets. We have a set of the people who won medals for slalom, set of the U.S. athletes, we've got set of gold medal winners, also set of Norwegian, and set of bronze medal winners. Now, we're going to try to figure out which one of these statements are true. Using this diagram, we may be coming back and forth to this diagram to figure out what's going to be true. But what is true? Is A a subset of G? We're wondering about it, for example. Is A a subset of G? So is the set of American athletes, is the set of American athletes a subset of the gold medal winners? Is it a subset? Where do we have some American athletes? We've got this guy, American athlete, also Hannah Kearney, also Merrill Davis. Those are our, that would actually be our set A over here. And so something we could do is we can use our Venn diagram. We can draw A as being the person David Wise, and then there's also, who else is in there? There's the person Hannah Kearney. And let me move these on the other side. We have David Wise, we have Hannah Kearney, and then we also have such a person as Merrill Davis. That's our A set. But then what if we wanted to draw our G set, which is the set of gold medal winners? Then actually, this is where they would overlap, because these two people are American and they won the gold medal. Hannah Kearney, she would be outside of G because she got the bronze, But then the G set, you notice it would have some other people in there. It would have Matthias Meyer, it would have Tina Mays, it would have Anna Haag, for example. These people would be inside of here. Matthias Meyer, for example, Tina Mays, and then also Anna Haag. Those would be people inside of there. But notice, if it was going to be a subset, then this A set should be completely inside of G. We should have an example where there's like the G set and then the A set is just inside of there. And then it would be a subset. But since the A set is kind of hanging out over here, then it's not a subset. That would be a way of thinking about this one. And then you could try these other examples. For example, whether the Norwegian people is a subset of bronze, or whether the Norwegian people are a proper subset of bronze. And then, lastly, we're throwing in here just a little fun fact. The number of subsets that you can actually make from a set, if you have a set that has k elements, you can make 2k subsets. And so, for example, if something has 2 elements, we're expecting to be able to make 2 squared, which is 4 subsets. Can you see which ones you can make, which ones would be subsets of this? Always, there's another fun fact here. The empty set is always a subset of a set A for every set A. So actually the empty set would be a subset of our little set that goes 1, 2. And then, what else do we have? We have the number 1 is a subset of there. It should really be a set though, with 1. This is a subset of the set that goes 1, 2. Also, we can make it go 1, 2, just have the whole set. That would be a subset of the set 1, 2. And then what about just the set with 2 in there? That would also be a subset of this one that goes 1, 2. And that would be all of them. Sure enough, there's 4 of them. And this is kind of a pattern that follows. We also always have that A is a subset of A. So that's how we got these 2. But anyways, this is kind of a counting problem as well. We're going to talk about counting and stuff like that quite a bit later in the trimester. So this will be something we'll revisit about counting, for example, the number of subsets of a set. But anyways, that does it for this video. I hope it was helpful for you all, and I will catch you in the next one. Thanks, bye.